So it became clear to me at the end of the last class that, and this is my fault, I was not as clear as I could have been about the structure of an ellipse. And I realized that I did write something in the notes that was a bit misleading, and I apologize for that. Because when I showed you the equation for an ellipse in the notes, I implied that a squared, the bigger of the two numbers, was always under x squared. And I completely forgot to write down this equation as well, which explained that the bigger number could also be under y squared. And some people got confused by that at the end of class. They were asking me, wait a minute, what's going on with this? And then I realized that was my fault, that I did not explain it well. So that's on me. So what happens is, everyone, is we have x squared and y squared, both in the numerators. We got a plus in between. We got a 1 on the other side of the equation. But there's no rule about which one has the bigger number underneath it. Either one could have the bigger number. Either one could have the smaller number underneath them. Either way. And what happens is the number under x squared always tells you how to move left and right, and the number under y squared always tells you how to move up and down. So if the bigger number is under x squared, then you're going to have an ellipse that looks kind of like Ernie, like this, a horizontal ellipse. And if the bigger number is under y squared, then you're going to have one of these that's kind of a vertical ellipse, shaped like a bird. So it just depends where the bigger number is, will tell you if it's a short, fat, or a tall, skinny ellipse. But it's always the number under x squared that tells you how to move left and right, and it's always the number under y squared that tells you how to move up and down. And a couple people stuck around at the end of class last time and asked a couple questions because they were very confused by this last example I did, and I was trying to figure out why they were confused, and I realized it's because I implied during the lecture that the bigger number was always under x squared, but that's not the case. The bigger number can be under y squared. So this is just kind of a summary of understanding the bigger number and the smaller number, where they are and what they make happen. So I made this ahead of time so it would be in your notes, and it just kind of explains how to draw an ellipse based on where the numbers are located. So that's in your notes, so you can look at that later. Everyone okay with that? This is the definition that you find in the book. This is the definition, and it's actually very, very clear. The reason I didn't just rely on their definition is because their definition talks about these things called foci, which are important to us, but we have not covered them yet in this class. You may have seen them when you're looking at the homework, or you may have seen them from looking at the book, but I have not covered them yet. So not covered yet. We'll get to that pretty soon today, actually. It's going to be one of the first things we talk about, but we have not covered them yet. So what this page of your notes is going to be really, really good for is just a really great summary on how to remember how to draw an ellipse and what gives it its shape. Okay. So that being said, let's look at an example together, similar to the one we did at the end of class last time. Give an equation for an ellipse with vertices -13, 0, and 13, 0, and a minor axis 20 units long. Now let me give you my two big tips for when you're trying to write the equation of an ellipse. There's two things that really help me when I'm trying to do this. The first thing is I remember what an ellipse equation looks like. My ellipse equation is going to be x squared over something plus y squared over something equals 1. And my job is just to figure out what those two somethings are. Then it's not as daunting as having to write down a whole equation. You just got to figure out what two different numbers are. That's it. The other thing that helps me write the equation when I'm trying to come up with the equation of an ellipse is I draw a crude, not perfect, but crude drawing just to give me the general idea of what's going on. For instance, this tells me that the vertices are at -13, 0 and 13, 0. So without worrying too much if I'm putting these in the perfect location, just making sure I get them on the right axis, I put in my two vertices. And if those are the vertices, then this right here is the major axis. And if that's the major axis, then the minor axis is shorter and goes up and down. Now the minor axis is 20 units long. So how far does it go in each direction? 10. So that means I get these ordered pairs right here at 0, 10, and 0, negative 10. And I think this picture is just for you when you're drawing it, just to help you figure out what's going on. But that should give you enough information to fill in the two boxes. Because from the center, you're going left and right 13, and from the center, you're going up and down 10. Now all you have to do, remember to do, is to square those numbers. So, because this right here is 13, that means what goes under here is 13 squared. And because this number right here is 10, that means what goes underneath there is 10 squared. And that's actually a correct answer, everyone, but it's probably a bit more traditional to actually square the numbers and write them underneath. So when someone asks you to write an equation of an ellipse, don't freak out and say an equation where to begin. The place you begin is to know what an ellipse likes and realize you need to figure out two numbers and put them in the right places. Any questions or comments about that problem? Yeah? If we did this one, definitely not on a test. I don't know how the online homework feels about that. Definitely on a test, this is 100% correct. And if for some reason on a quiz you did this and it told you you were wrong, that's what you shoot me an email about and say, Steve, I had the right answer, I just didn't like the way it looked. Everyone cool with that? All right, what else can we do? What else can we do? What if my ellipse equation does not look like an ellipse equation? Well, the center is always going to be at 0, 0. So they can't mess with it too much, but here's a way they can mess with you. This is actually the equation for an ellipse, everyone, but it doesn't look like an equation for ellipse. Because with an ellipse, we have fractions over on this side. Does everyone agree with that? And more importantly than having fractions on that side, which actually is not the most important thing, the most important thing is actually what number is supposed to be over here. And what number is supposed to be over there? A 1. This should be a 1. Don't subtract 143. That would be one way to try to do a 1, but that's not the way you want to do it. You want to divide by 144. So if the number over there is not a 1, you divide. And if you divide, you're going to get this. And I know some of you can do a lot of mental math and you don't have to show every little step, but of course when I do an example, I like to show every step. And if I divide both sides by 144, then this side will become a 1. The problem with this now, everyone, and as I said on this first example of this, I show every little step just so we're all clear on what's happening. What I say is, I don't want 4x squared, just x squared. I don't want 9y squared, just y squared. So what you do is you leave x squared and y squared alone, but divide both top and bottom of each fraction by the coefficient in the numerator. And once again, the words are a lot more complicated than what you actually have to do. Usually what we have to do in math, it's much easier to see it with an example, but I still want you to have the words in your notes. So what we have to do here to reduce these is you take the 4 over 144 and you divide both the top and the bottom by 4. You take the 9 over 144 and you divide both the top and the bottom by 9. Even if it doesn't divide evenly into the bottom, you still need to divide by that because you need to get rid of the number on the top. This is how you reduce those fractions. This is the only way that's going to get your ellipse in the proper form. Now if you do that, what you'll end up with is you'll end up with just an x squared on top and just a y squared on top. And of course the 1 on the other side. Then, either doing math in your head because you're awesome with your multiplication and division, or reaching for the calculator, you do 144 divided by 4 and 144 divided by 9. And what's 144 divided by 4? 36. And what's 144 divided by 9? 16. Math, more enthusiasm. So much fun. And then it looks like a regular ellipse. Now, when you do this the second and third and fourth time, if you do this a bunch of times, you're not going to have to write down all of this every time. But I wanted to write down everything this first time so you'd understand the steps. And now, we have an ellipse we can work with. Cool or not cool?
And then the radius for that one on the x would be 6.
So if this one, if you were going to graph, we don't call it a radius, but we would say left and right 6, up and down 4. That's how you get your 4 points. Absolutely. Okay, so let's draw an ellipse together, everyone. Let's draw an ellipse. Oops, I thought I'd already copied this. Copy, edit, paste. And I'm going to do this in a nice big one because I'm actually going to draw on this graph a little bit. I'm going to add some stuff to this graph after we draw our ellipse. So here's what I want to do. I want to do x squared over 16 plus y squared over 25 equals 1. And this is not a trick question, everyone. This is just drawing an ellipse like we did last time. So you take the square root of a number under x squared. That will tell you how far to move left and right to get 4 points. I'm sorry, to get 2 of your points. And then you take the square root of the number under y squared, and that will tell you how far to move up and down to get 2 more points. I'm not saying everyone's an expert yet. We're still practicing this. We're still learning this, but this is what we did last time. So we can do this. So I'm going to go left and right 4, up and down 5. And then I will do my best, which is not always amazing, but I always try, to get an ellipse. And what I want to make very, very clear to you, no matter what I'm going to talk about next, I am going to make this a bit more complicated. The way you draw the ellipse, your initial ellipse, is not going to change with what I talk about next. Is everyone okay with that? Here's what I want everyone to do. I want you to look at the numbers that are under x squared and y squared. And I want you to subtract the smaller one from the bigger one. Whatever those two numbers are, I want you to do the bigger minus the smaller. For those of you who remember our lecture from last time, that's the same thing as me saying this to you. A squared minus b squared, because a squared is the name of the bigger number and b squared is the name of the smaller number. You're going to do a squared minus b squared. And of course, if you do that, what do you get? 9. Now, this is going to bother some of you. This 9 is actually a number that we call c squared. And the reason that bothers people is because a lot of people are used to a squared plus b squared equals c squared. They're used to the Pythagorean theorem. This is not the Pythagorean theorem, this is an ellipse, everyone. So a squared minus b squared does equal c squared, and this is not a mistake. I don't want you looking at this later and saying, did he mean to write minus there? Didn't he mean plus? No, I meant minus. Now I want you to take the square root of that number. And of course, that's going to be 3. Now this is where ellipses get more complicated, so I'm going to need you to bear with me as best you can. Is the major axis on this up or down, or is it left and right? Up and down. Are the vertices up and down or left and right? Up and down. Everyone cool? Why? Because that's the longer way. So, make 2 more points this far from center in the same direction as the vertices on the major axis. So that number that we just got, that 3, you're going to make 2 more points on your ellipse. And they're not going to be on the ellipse itself. They're just going to be in your graph. You go in the same direction as the vertices, and you go that far from the center in each direction. So in the case of this ellipse, I am going to go up 3 and down 3. These 2 extra points that are not on the ellipse itself are called the foci, which is the plural of focus. I would much rather say focuses, but they're not. They're called the foci. Each one of those is called a focus of the ellipse. Each one of these is called a focus of the ellipse.
What's being focused?
Well, that's a good question. Can someone tell me what a circle is, besides just saying it's a round thing? What is a circle? I'll get you started. It's all the points
Equidistant from a single spot.
equidistance from the center. And what do we call that distance?
Radius.
The radius. A circle is all the points, the same distance, called the radius, from a central point called the center. Does everyone agree with that? That's what a circle is. A dog can make a circle. You just put a dog on a rope, a nice soft rope, or being nice to the dog. You tie it to a stake in the yard, let it run around in the snow. It'll make a circle. The rope being the radius. These foci right here are actually what gives the ellipse its shape. These are what define an ellipse. So, here's what an ellipse is, everyone. An ellipse is a conic section such that every point on the ellipse is some distance from each of 2 foci. The sum of those distances is the same as the length of the major axis. And I do not expect all of you to love that statement when you read it. An ellipse is a conic section such that every point of the ellipse is some distance from each of 2 foci. The sum of the distances is the same as the length of the major axis. Now I'm going to make this as clear as I can here, everyone. And I'm going to copy this thing here and bring it down here so I can talk about it more clearly. No, everyone, everything. Awesome. Except I don't think I'm going to keep my grid. That's okay, I actually don't need it. Oh, I did keep my grid. Superb. All right, everyone, watch this. What is the length of the major axis for this ellipse? 12. No, sorry. 10. That's okay. 10. All right, now watch this, everyone. I'm going to pick some random point on the ellipse, and I do truly mean some random point. Right there. That's a point on the ellipse. Now, here's what I'm claiming. You call that one D1 and that one D2. D1 plus D2 equals 10. That's actually what gives an ellipse its shape. Is that every point on the ellipse has a distance to one focus and it has a distance to the other focus. And the sum of those distances is always the same as the length of the major axis. It does not matter what point you pick on the ellipse. I could pick this point right here. And I would draw that, and I'd draw that. And I'd call that D3, and I'd call that D4. And class, what is D3 plus D4 going to be? 10. That is what gives an ellipse its shape. There's actually used to be an illustration that they put in math books where you take like a piece of paper, and what you do is you put like a thumbtack in the paper here and here, and you put a loose loop of string between them. And then you take a pencil and pull it taut and draw it around like this. And actually what that would do is that would create an ellipse. I pity the people that look at these notes afterwards and don't know what I'm doing. Because they're gonna look at that, they're gonna be like, is Steve on a treasure hunt? Is that a map? But that is how you draw an ellipse, because that distance is gonna stay the same. So the distance of the major axis is always the sum of the two distances for every point on the ellipse. Now, let me be very clear. We don't need the foci to sketch our graphs, but they are part of the structure, so we need to understand them. But don't let this get in the way of you drawing a picture of the ellipse. Don't let this keep you from feeling like you understand how to make one of these ellipses. Just know that these are what gives the ellipse its shape. It's not just some random oval I might draw. It actually does have a structure to it, just like a circle does, just like a parabola does, just like an exponential function or a logarithmic function. They have a structure. They follow a set of rules. And this, while being a little bit cryptic and difficult to read through, is the rule for the structure of an ellipse. Okay, let's draw another ellipse. Let's go x squared over 100 plus y squared over 36 equals 1. And fortunately, oops, don't need that anymore. And fortunately for us, my coordinate system is just barely big enough to fit this on here. Now, even if you didn't understand a thing I said about foci on the previous page, can you still draw this ellipse? Yeah, let's do that. Let's do that. We'll go left and right 10. We'll go up and down 6. And we'll try to keep from making ourselves completely miserable drawing this thing. The secret to finding the foci is doing the bigger minus the smaller. There's always going to be one that's bigger, there's always going to be one that's smaller. So what subtraction problem am I at to do? 100 minus 36 equals what? 64. It's almost like I planned ahead. Because the square root of 64 is what? 8. Now, the foci are always on the major axis inside the ellipse and the same distance from the center. So the foci from this are on the major axis, the same distance from the center. Right here and right here. So they are going to be at plus or minus 8, 0. Here is some random point on the ellipse. Without anyone saying it out loud, everyone write down what D1 plus D2 is. No one's saying it out loud, everyone write it down. No one's saying it out loud. Everyone's just writing down what D1 plus D2 is. And what is it? I haven't heard it yet.
Would it be 20?
It is 20. Because, and it's okay, we're just learning this, so I don't mind that anyone gave a wrong answer. I like that you're trying. But it's the same as the length of the major axis. And does everyone agree that the major axis for this one is 20 units long? That's why it's 20. That's why it's 20. Sometimes foci are closer to the center, and sometimes they are closer to the vertices. The closer to the center they are, the more circular the ellipse. In other words, class, there are some ellipses that look much narrower than other ellipses. And so what I'm trying to say is the closer the focus or the foci are to the center, the more it will look like just a regular circle. But there's no rule about if they're closer to a vertex or closer to the center. The only rule is they are the same distance that you get when you take the square root of a squared minus b squared. That's how we find our foci. So we can actually do this without even drawing the ellipse. So if someone wants the foci for this ellipse, here's what I'm thinking to myself. I think I need to do a squared minus b squared. If that makes me uncomfortable, I just remember that that means do bigger minus smaller. Either way, if I want the foci for this ellipse, what am I doing? What minus what? 49 minus 16. We cool with that? 49 minus 16. And that's going to give me 33. If I want to know where they are, then I have to take the square root of that number. Don't reach for the calculator. You want to write square root of 33. That's the right way to write it. Then I do this, and see if you follow this line of reasoning. The bigger number is under y squared. So the major axis is up and down. The foci are up and down. So the foci are 0 plus or minus whatever I got for C. If the major axis is up and down, the foci are up and down. And if the foci are up and down, then the ordered pair starts with a 0. And in this case, they're irrational. But when you're doing your homework for this, they're going to want the exact answer, not a decimal approximation. They're not going to want you to plug that into a calculator. They just want you to say 0 plus or minus the square root of 33. That's where they are. C squared is found by doing a squared minus b squared, the bigger minus the smaller. Then you take the square root of that number, and that tells you the distance from the center to a focus. And the focus, the foci, same direction as vertices on the major axis every time. Okay. Well, I'm okay. Are you all okay? All right. How about this one? A little side note for everyone here. Math homework wants an exact simplified answer. So, let's say you're doing a problem and you get that C is the square root of 45. You get that the foci are square root of 45. And you know that the major axis is left and right. What you would write then is you would write that the foci are at plus and minus the square root of 45, comma 0. Why? Because C tells you how far to go, and since the major axis is left and right, that means the foci are left and right. They are always on the major axis, never the minor axis. And the math homework will freak out on you if you put that answer. They'll give you one of the more annoying messages that says, even though your answer is equivalent to the correct answer, it's not in the proper form. Because they want you to remember that square root of 45 is the square root of 9 times 5, which is the square root of 9 times the square root of 5, which is 3 times the square root of 5. So they actually want you not to reach for the calculator, but to reduce and simplify your answer. Which I will not say is my favorite thing to do, but that's what they want you to do. So if you're missing these problems, it's not because you should have turned it into a decimal, it's because you were supposed to try and reduce it down. Okay. Now we can do some problems called Stephen's secret ellipses. Now, when I say we're going to be giving the equation of each ellipse that I describe, if I say we're going to give an equation of an ellipse, you already know the game. You already know you're going to be doing x squared over something plus y squared over something equals 1. Your job is to find a squared and b squared and put them in the right places. In other words, you have to find the bigger number or the smaller number, and you have to make sure you put the bigger number under the proper x squared or y squared, and put the smaller number under the right one. That's what you have to do. If someone wants an equation for an ellipse, this is the universal task that those instructions mean. We just need to watch out for what they're going to say to us. Sometimes the instructions are easier than other times. For instance, vertices at 4, 0 and negative 4, 0, endpoints of minor axis at 0, 3 and 0, negative 3. We sketch a little picture to help us. I see that I'm going left and right 4, up and down 3. I drop in my two numbers 16 and 9 because I'm going left and right 4, so square that you get 16. Up and down 3, square that you get 9. Since it was left and right 4, that's why the 16 goes under the x squared, and since it was up and down 3, that's why the 9 goes under the y squared. This is like the problem we did at the very end of class last time, and one of the problems we did earlier today. What makes these trickier is this one basically gives you A and B. They basically tell you A and B because they're giving you that 4 and that 3. But on other problems, they give you A and C, or B and C. And you need to use A squared minus B squared equals C squared. So that's what's going to make these problems trickier. That's what's going to make them harder, is they're not going to tell you A and B. They're going to tell you A and C or B and C. And then you got to use this relationship of A squared minus B squared, bigger minus smaller, to find the missing letter. I'm not saying this should be perfect for you right now. I'm saying this is what's going to make these problems trickier for us. So let me show you one that's trickier. This is a trickier problem, everyone. This is a trickier problem than the one we just did. But I will not forget my mission parameters, and that is, I want that, and it helps to draw a picture. The vertices go left and right, 13 units each. The foci go left and right, 12 units each. This does not give me A and B. What two letters is it actually giving me?
A and C.
It's giving me A and C because distance to vertex is A and distance to focus is C. So this is actually telling me that A equals 13 and C equals 12. It does not tell me B directly. What is A squared, everyone?
169.
169. What is C squared, everyone? 144. In general, the relationship between A squared, B squared, and C squared is this. So therefore, 169 minus B squared equals 144. From this information, can we figure out what B squared is? Yeah, I don't really want to. I guess I'll subtract 144 from both sides and add a B squared to both sides. And that's going to give me 25 equals B squared. Bingo. Look at this board, everyone. Look at that board. Do I have the number A squared? Do I have A squared? Yeah, it's 169. Do I have B squared, everyone? Yeah, it's 25. The only thing you need to figure out now is you got to make sure you put them in the right places. Did I go up and down 13 or left and right 13? Left and right 13. Oh, math. Those are hard. I'm not going to sit up here and tell you they're easy because you'd see right through that. You'd say, that's not an easy problem, Steve. Maybe some of you get it faster than others because you're better at the visual learning with the ellipse and stuff like that. That's great. But if you're stuck by that, please don't think that that's an easy problem. There's a lot of stuff you have to keep track of. What helped me do it? Keeping my eye on the prize. I needed 2 numbers. What else helped me do it? I drew a picture to help me. What else? I figured out what I was dealing with. I didn't just say, here's a couple random numbers. I said, they're giving me A, they're giving me C. I need to find B, or B squared, more importantly. All right. Let's have you try one. You want to try one of these? All right. Minor access is 6 units long. Foci are at 0 plus or minus 4. Give the equation of the ellipse. Minor axis is 6 units long. The foci are at 0 plus and minus 4. And remember, don't just stare at this and wonder what to do. Start sketching a picture. Start focusing on finding A squared and B squared. I probably gave you one of them already. And writing down the equation. Once you have it, write it down. Don't shout it out. Everyone go ahead and when you finish that first one, try the second one. And we're going to start class up again in about 13 minutes at 11:32. So take about 3 minutes to work on this, and then you can go to break. If you don't finish it, you can still go to break. So hopefully you had some time to work on at least the first one here. So I think the secret to figuring these out is, knowing that you're just looking for 2 numbers and also to draw a picture. So I'm going to start by drawing a picture. Now here's the thing. Just reading that the minor axis is 6 units long does not actually tell me where the minor axis is, just that information. So what I actually need to start with on this first one is where the foci are. And they are at 0, plus and minus 4. So when I start my picture, I put my foci up here at 4 and down here at negative 4. But if that's where the foci are, that means the major axis goes up and down. Does everyone agree with that? So if the major axis is up and down, that means that the minor axis is left and right. So now I know where the minor axis is. It goes left and right. So if I'm thinking about my equation over here, I got x squared plus y squared equals 1. I can actually fill in one of those numbers right now. What number can I fill in and where can I put it?
3 squared on x squared.
I can put the 3 squared underneath x squared because I'm going left and right 3. And since it's left and right, that means it's under x squared. And because it's 3, that means it's 9. So this right here is enough to tell me that I put a 9 underneath there. Now, I know from that b squared is 9 because b is associated with the minor axis. I know that c squared is what, class? Anyone know what c squared is?
16.
It's 16, and because this distance right here to focus is c, so therefore c squared is 16. This distance right here to an endpoint of the minor axis is b. Does everyone see how I know that's c and c squared? Because c is always associated with how far the foci are. Everyone cool with that? And b is always associated with how far it is to the endpoint of the minor axis. Now, what's my special relationship between a squared, b squared, and c squared? What's the equation?
A squared plus b squared equals c squared.
A squared minus b squared equals c squared. I know it's hard because it's not the Pythagorean theorem. It's slightly different. So that means we're going to have a squared equals c squared plus b squared. Oh. A squared equals c squared plus b squared. Wait a minute. Do I know b squared? Do I know c squared?
9, 16.
Yeah, it's going to be 25. So the question is, what do I put under here? Do I take the square root of 25? Do I square it, or do I leave it as 25?
You can leave it as 2.
I leave it as 25 because this is a squared. And we're done. X squared over 9 plus y squared over 25 equals 1 is the ellipse that has a minor axis 6 units long with foci at 0, plus or minus 4. Let's look at this one right here. This one looks kind of annoying. Major axis is 18 units long. That doesn't help me yet. Foci, though, are to the left and right. So if the foci are to the left and right, I guess square root of 77 and negative square root of 77, that's a bit annoying. And the major axis is 18 units long. Are the major axis and the foci always in the same direction? Always? Always. So that means that out here, I have a vertex, and out here I have a vertex. And how far is the vertex from the center? 9, because it's 18 altogether. All right, so what do I know? What do I know?
A squared.
Yeah, I know that A is 9, because that's the major axis, therefore I know A squared is 81. I know that C equals the square root of 77, and therefore C squared is just 77. Can I start to fill out anything on the equation yet? Yeah, what can I do? Very good. Why? Because I went left and right 9. 9 squared is 81, so that goes under the x squared. It's exactly because that was a 9 and I squared. Then I guess I need to know that a squared minus b squared equals c squared, or let's see here, this one's a little bit trickier. I gotta do a squared minus c squared equals b squared. If you manipulate the equation by adding b squared to both sides and subtracting c squared from both sides, that's what you'll get. 81 minus 77, b squared equals 4. Now, the mistake a lot of people make when they get this number is they think something like, am I supposed to take the square root of it, or do I need to square it? No, you don't need to do either one of those things. It's already b squared. And since it's already b squared, that's why we put a 4 under there. If you got these, great. If you didn't, don't feel bad. They take practice. They absolutely do take practice to do them. How'd we do? Did we do okay? So, I'm going to skip the truck in the tunnel problem from the homework because it is not on the exam. You can fight through the homework. It's a tricky story problem, everyone, but I'd rather talk more about hyperbolas than do a story problem right now. So I'm going to skip that problem. And when you're doing it in the homework, rest easy. I'm not going to put the truck through the tunnel problem on the test, and you'll know it when you get to it because you're driving a truck through a tunnel. Fight your way through it as best you can on the homework. Ask people for help, get help however you can, and just do your best with it. But then rest easy that it's not going to be on your exam, not even as an extra credit or anything like that. Okay, and we're going to go ahead and say done with ellipses. I could actually talk about ellipses for the rest of the class today and for more of class after break, but we don't have the time. We're going to move on to conic section number 3, which is the hyperbola. Which is a graph in 2 pieces that is not 2 parabolas. The hyperbola is another conic section. It is a graph made up of 2 separate pieces that do not touch each other, and it is not 2 parabolas. A hyperbola is not a function in section 10.3. We are going to learn about hyperbolas, and they are not going to be functions. The reason for that is a hyperbola either looks like this, and that is one hyperbola right there, everyone. One hyperbola has 2 pieces to it. Or, where did the attendance sheet not get to? That is one hyperbola, everyone. It is not 2 parabolas. It's not 2 hyperbolas. It's one hyperbola. This right here is also one hyperbola. But you can see no matter which one you're looking at, it fails the vertical line test, so it's not going to be a function. Okay. Usually what I do, and it's kind of up to you, well, as long as you're clear, but I usually call this one a left and right hyperbola because I talk about the way it's opening to the left and right. And I call this one an up and down hyperbola. There was one semester that I tried to call them TIE fighters and X-wings, but that just messed with people's heads too much, so we're not going to do that. So we're going to call them by the way that they open. They either open to the left and to the right, or they open up and they open down, and that's where they come from, or that's what they look like. In our second unit, we saw a hyperbola that was a rational function, it is not covered in 10.3. We will look back for just a moment. We actually have seen a hyperbola in this class before, and we have drawn a hyperbola, and a hyperbola actually showed up on one of your tests, but I never called it a hyperbola. But this hyperbola is a function, and therefore we do not talk about it in this unit, except to say that we remember it. If you tilt your head 45 degrees, you can see this is like a diagonal hyperbola. So we called this our most basic rational function, or the inverse function, but it is actually a hyperbola, but it is a different type of hyperbola. Ours will not look like this. But it's kind of nice to know that we've seen them before. And was this considered one graph, everyone, even though there were two pieces to it? Same thing. This is considered one graph, even though there's two pieces. One graph, even though there's two pieces. What's this thing?
Ellipse.
That's an ellipse. Yeah, that's an ellipse. Oval. What's this one, Mr. Roundy? It's a circle. Yeah, that one's a circle. Okay, here's a hyperbola, everyone. Or what a difference a minus sign makes. This is a hyperbola. Hyperbola equation looks just like ellipse, except ... Here are the differences between a hyperbola equation and an ellipse equation. Hyperbola will have one minus sign, never two. So they won't both be negative. You'll have one minus sign in a hyperbola. Hyperbola will have one minus sign in it. Because the minus changes things, x squared or y squared might come first. In other words, with an ellipse, because it was a plus sign, we always wrote the x squared first because it didn't matter. But with a hyperbola, sometimes, so the y squared has a chance to not have the minus sign or to be the first term, we write it with a y squared first. So with a hyperbola, occasionally the y squared will come first. Actually, just as often as the x squared comes first. The numbers under x squared and y squared could be the same. Because it's the minus sign now, it's not going to be a circle if they're the same. It's just going to be a different looking hyperbola. So the numbers underneath x squared and y squared could match exactly, and it's still a hyperbola. So those are our big differences. You need that minus sign. You need the 1 on the other side, and the numbers could match. People can be jerks. Do you think that's a hyperbola, everyone?
No. Oh, well, yes.
Yeah, that's what I mean. People could be jerks, right? They could write it in the wrong order. What matters is that one of them is negative and one of them is positive. So that's still a hyperbola. Well, I like this part of the lecture. Let's continue with people can be jerks. Let's do this one. Oh, let's do this. 9x squared. That's a hyperbola also. That's a hyperbola also. It's an annoying hyperbola, but it's a hyperbola. Because you could divide everything by negative 144. Everyone with me so far? If you divide everything by negative 144, this side becomes a 1, just like a hyperbola should have. We reduce these fractions the same way we reduced them back when we were doing ellipses. So, we take negative 9 over negative 144 and divide both the top and the bottom by negative 9. We take 16 over negative 144 and divide both the top and the bottom by 16. What that will give us when the dust settles is x squared over 9 minus y squared. I'm sorry, it will give us x squared over 16. Apologies. Minus y squared over 9 equals 1. So sometimes people give us hyperbolas that don't look quite like hyperbolas, but they are still hyperbolas. This didn't look like one when we started with it. This one didn't really look like one. But as long as we can get that 1 on the other side, we get that 1 minus in there, we're looking at a hyperbola. Hyperbolas are harder to draw than the ellipse and circle. But there is still a trick to drawing them. And it still involves the square root of the numbers under x squared and y squared. These are harder to draw. They take longer. There's more to worry about, but there is still a trick. And the trick still is about the numbers under x squared and y squared. Hyperbolas are different than ellipses and circles, obviously, because they look different, but also because they're not nice and contained like ellipses and circles. These things go off in all directions at once, and we need to be aware of that when we sketch a graph. So in general, the graph is much larger because it just keeps going and going and going. All right, let's graph a hyperbola. First of all, the reason this is a hyperbola and not an ellipse is because we have a minus sign there. And just like the ellipse, this is always going to be the number 1 over here, always. What I want you to do is I want you to make 4 points as if you were going to draw an ellipse, but don't draw the ellipse. But I want you to make 4 points as though you were going to make the ellipse by doing the square root of the number under x squared and the square root of the number under y squared. Just like you were going to make an ellipse, you make your 4 points, but then don't draw the ellipse, because this is not an ellipse. So we are going to go left and right 4. Because the square root of 16 is 4 and it's under x squared. And we're going to go up and down 3, because the square root of 9 is 3, and it's under y squared. Did everyone get those 4 points okay? What we're going to do now is we're going to draw a dashed line box, and you should do it with dashed lines, as though you were drawing an asymptote. And your dashed line box should pass through all 4 of those points. Each point is the midpoint of a side. That's how you know where they are. Each point that we drew is the midpoint of one side of that rectangle. This is actually called, and I don't use this term as often as I should, this is actually called the fundamental rectangle. And the reason we're doing it with dashed lines is because that's not the hyperbola yet. You know what a hyperbola looks like, those 2 huge curves. This is not a hyperbola. And we're going to draw something else that's dashed, everyone. What you have to do is this. Through the corners and center at 0, 0, because just like ellipse, all centered at 0, 0 in Math 121. Just like the ellipse, we're going to center all these at 0, 0. Through the center at 0, 0, and the corners, draw 2 diagonal asymptotes, or slant asymptotes. Through the corners of the box and through the center of the hyperbola, you're going to draw 2 long diagonal slant asymptotes, like that. You must go through the corners of the box. You must go through the center of the box. You must. That's still not the hyperbola, but don't worry, we're almost there. Here's the rule for a hyperbola, everyone. The hyperbola either opens left and right, or the hyperbola opens up and down. One of those 2 things. The way you know which way it opens is by looking at which term came first. If it was the x squared term that came first, it was the positive term, then you're going to open left and right. If the y squared term came first, and it was the positive term, then you're going to open up and down. So which way is this one going to open? If the x squared term is first and positive, we open left and right. If the y squared term is first and positive, we open up and down. This one's going to open left and right. I know I talk fast. I'm sorry. I don't mean to put you all on the spot like that. Are we okay with this one opening left and right? Touch points on the box, the fundamental rectangle. Hug, but don't touch the asymptotes. This is tricky, everyone. You're supposed to touch the points on the box, which is the fundamental rectangle, and you're supposed to hug, but not touch the asymptotes. And I'll show you what I mean. Touch the points on the box. Well, let's try this.
Oh, not the corners.
There's the hyperbola. There's the hyperbola, everyone. You touch the box. You touch the box. You don't touch your slant asymptotes. You just hug them. You get close to them, just like you do with an normal asymptote. Hug it. That is how we draw a hyperbola. That is not the only way to draw a hyperbola. That is how I've been teaching how to draw hyperbolas for years. That is how most textbooks teach you how to draw it. Almost every algebra textbook you look in will show you how to draw this box. Draw in those diagonal or slant asymptotes, and then sketch in the hyperbola afterwards. If you look up a picture of a hyperbola on the internet, it's probably going to show it with this box in the middle of it. It's just how we do this. Would you like to do another one with me? Warning, for a hyperbola, y squared could be first. And the number under y squared still helps you move up and down, whether it's first or second. Everyone, this is very, very sneaky. With an ellipse, we always wrote x squared first. With a circle, we always wrote x squared first, because there was a plus sign and it didn't matter which one you wrote first, so we always wrote x squared first. With a hyperbola, sometimes y squared comes first. And if y squared comes first, you're still using the number under y squared to know how much you should move up and down. So I'll help you with that right now. All of us, based on all the math we've been doing for the last 2 days, are used to looking at the first number to see how far we should move left and right. But for this one, since the square root of 4 is 2, we move up and down 2 because it's under the y squared. And we move left and right 3 because we're under the x squared. It is so easy to get that backwards. Because with every ellipse we do, we always wrote x squared first. Is everyone going left and right 3 and up and down 2? Once you do that, you draw in what we call the fundamental rectangle. One of my favorite teachers at this school is this guy named Steve Wolf. And he has the driest sense of humor that like no one laughs at in his class, but I was watching him teach once, I was laughing the hardest because he was talking about how he loves the fundamental rectangle so much he has a pillow at home shaped like it. And his class was looking at it like he was out of his mind, and I'm just giggling in the back row at math jokes. Once you get that fundamental rectangle drawn in there, you do those diagonals, make sure you're going through the corners of the rectangle. That's how you guide yourself. You go through the corners of the rectangle. And because the y squared term is first, that's actually what tells you that this hyperbola opens up and down.
Is it only because it's first?
That's right. It has nothing to do with which one's bigger.
With negativity, positivity?
Oh, no, I'm sorry. What happens is the positivity is what matters. But we almost always write the positive one first unless we're being jerks. So you're absolutely right. What I should say is it has to be the positive one. It's just that I always write them with the positive one first, but you're absolutely correct. There's our hyperbola, everyone. The hyperbola does keep going forever and ever and ever. That's why I put the arrows on the end to show it keeps going forever and ever and ever. Everyone agrees that this is not a function, hopefully, because it's got these two different pieces. Even though it's not a function, you can actually write the domain and range of one of these. Let's see if we can do that. I want you to look at that thing. Does it go left and right forever? And no gaps in the middle. So this thing actually has a domain of negative infinity to infinity. It does truly go left and right forever. And the thing is, even though it does go down and up forever, there's a gap in the middle. There's a gap in the range. So it does go down to negative infinity, and it does go up to infinity, but the range takes a break in the middle. Between which two y values does it take a break? -2 and 2. Does everyone see that? There's a piece missing in the middle, vertically. Let's go back to our previous hyperbola for just a moment and jot in the domain and range of that one. We can put it right on the graph. Which has a gap in it, the domain or the range? Which one has a gap? The domain has a gap. Yeah, the domain for this one does go from negative infinity, and it does go all the way up to infinity, but it takes a break between which two x values? -4 and 4. But the range, there is no gap in the y values. So we can actually come up with a little rule for ourselves to help us do this. We can come up with a little rule to help us do this. It will look like this. If it's this kind right here, the range will be negative infinity to infinity, and the domain will be negative infinity to something, and then up to infinity, because it takes a break at the fundamental rectangle. And if it goes like this, then the domain is negative infinity to infinity. The range is negative infinity to something, and then something to infinity. But it takes a break at the fundamental rectangle. And even though this might not make a whole lot of sense at this moment, I'm going to put something in here for you, just so your notes are complete. We actually have a name for that. We call it A. Now, I have not explained what A means yet as far as a hyperbola goes. You might be thinking I explained them for an ellipse, and I did. But I have not explained them for a hyperbola yet. All right. If you are drawing a hyperbola, everyone, if you are drawing a hyperbola, then the points on the box that the hyperbola touches are each called a vertex. of the hyperbola. And once again, we have two of them, so we do have vertices. The points who are touching are actually each called a vertex of the hyperbola. The invisible line segment that makes those two boxes touch is called the transverse axis. We do not usually draw the transverse axis, but it is in there. It is a short line segment. Well, it doesn't have to be short, depending on the nature of the hyperbola, but it is a line segment that connects the two vertices. It is a line segment that connects the two vertices. One second. Which ones did I do? I did 4 and 9. I did 16 and 9. Let's do 25. And 64 would be a little big. Let's do 36. Oops, that's not a hyperbola. Why not? Oh yeah, I guess I need a minus sign in there. Okay, that's a hyperbola. Can we draw that one? Let's draw that. Let's draw that one. Make your 4 points. Draw your fundamental rectangle. Draw those diagonals going through it. And you can keep going if you want, but I'm going to stop there on purpose for a moment. And the reason I'm going to stop there is because I've wanted everyone, before I draw the rest of it, to write down what they think the ordered pairs of the vertices are. I want everyone to write down what you think the ordered pairs of the vertices are. And while you're at it, I want you to write down the length of the transverse axis. Before I even draw the hyperbola itself, I want you to write down where the vertices are, and I want you to write down the length of the transverse axis. Is this possible to do without me drawing the picture? It is. Well, there's 2 vertices, and there's 4 points to choose from. They're either going to be this one up here and this one down here, or this one on the left and this one on the right. Those are the 4 points I got to pick from. Which ones does it have to be, left and right or up and down? I hear left and right. Does anyone else say left and right? Why left and right? Because this one opens left and right. So as soon as I saw this hyperbola here, I thought to myself, this one opens left and right because the x squared is the first term, the positive term. That means that my vertices are right there at plus and minus 5, 0, or negative 5, 0, and positive 5, 0, however you wrote it. And once I know where the vertices are, do I also know where my transverse axis is? It's right here. This is the transverse axis. How long is it? 10. And I can draw in my hyperbola now. All right. There are only two vertices. The other way across the box, or the fundamental rectangle, is the conjugate axis. Not quite as important to talk about as the other one, but it does have a name. The other way across the box, or the fundamental rectangle, is called the conjugate axis. So I have a couple more things I need to tell you today. First of all, hyperbolas have two foci. We'll talk about those after fall break, but they also have two foci. But we won't worry about that today. Hyperbolas also call the numbers under x squared and y squared a squared and b squared, or b squared and a squared. They also call those numbers underneath, a squared and b squared. Now this is very important, everyone. This can ruin your day if you don't understand this. For an ellipse, a squared bigger than b squared, always. For a hyperbola, a squared is with the positive fraction, and b squared is with the negative fraction. It is annoying because they use the same vocab, but they follow different rules. And I know that's annoying. That's why I wanted to make sure I got this idea out to you before we went on fall break. For an ellipse, a squared is always bigger. I will keep saying that to you. But for a hyperbola, a squared is with the positive fraction and b squared is with the negative fraction every single time. Which one is a squared? 64 or 100? Which one is a squared? 36. All right, let's cool down with a summary. I made this myself, everyone, just for my math classes. I actually don't know if I got to everything on this yet, but if we don't, we'll get to the rest of it next time. Of course, you should not try to copy all this down because I'm going to add it to the notes and I'll post it after class for you. In Math 121, our hyperbolas will be centered at the origin, 0, 0. Equations for the hyperbolas will be of one of these two forms. You will notice no matter which form I wrote, I always put a squared with the positive term and b squared with the negative term. Does everyone see that? That's because a squared is not always bigger than b squared. There is no rule about which is bigger, a squared or b squared. They can even be the same size. A squared is under the positive, usually first term, and b squared is under the negative, usually second term. If x squared is our positive term, the first term, then the hyperbola opens left and right. Is that what we did today? If x squared is positive, usually a first term, our hyperbola will have its vertices left and right. If it opens left and right, the vertices are left and right. The transverse axis will be horizontal, connecting the vertices, which are left and right. The conjugate axis will be vertical. The other way across will be vertical. If y squared is our positive, usually first term, our hyperbola will open up and down. If y squared is our positive, usually first term, our hyperbola will have its vertices up and down from the center, the transverse axis will be up and down, and the conjugate axis will be horizontal. When drawing your dashed or fundamental rectangle, the square root of the number under x squared still always tells you how to find points left and right, and the square root of the number under y squared will still always tell you how to find the numbers above and below. Always. No matter which one comes first or which one comes second. By the way, everyone, the last thing I'll tell you before you get out of here is the way I remember which one's the transverse and which one's the conjugate is transverse has a v in it, and so does vertices. That's how I remember which one is which. You remember any way you need to. Are we done with hyperbolas? No. We'll finish them after fall break. Everyone, have a very happy and safe Thanksgiving.